Welcome to the ET335 lecture video on decoders and tristates. Okay, here I'm showing a three-state buffer called a tri-state. And this one's an active high enable because it doesn't have a bubble on it. So these bubbles aren't negating, they're telling us that they're looking for an active high or low, in this case high, enable to make it active. And these devices are used to allow information on one data bus. So these can't be on all at the same time, otherwise the data would crash on the bus. So we're only allowed to have one of these at a time. Here I'm showing an active high tri-state, and I'm going to show you the three states. The first state would be when we have a high enable. So high enable means it's active and it's going to pass data through it. So if we have a high enable, we're going to get a high on the input and high on the output. If we have a high enable, it's activated, and we're put a low on the input, we're going to get a low logic level out. If we put a low on the enable, it's going to be disabled. So it's going to be disconnected, or what we call high Z, high impedance. So it's going to act like an open switch and disconnected from the bus. So no matter what we put on the input, it's not going to pass any data. Here I'm showing an active low enable tri-state, and you see the bubble here, and this says that we're looking for an active low enable. So this one goes low, then this device will be activated. Okay, so here are our active low tri-states. Here, if we have a low enable, we're going to put a high input and we're going to get a high input. Again, these are not straight through. This is a logic device, so high will give us a high. If we're enabled with a low and we put a low on the input, we're going to get a low on the output. If we put a high, that's disabled. We're going to be disconnected from the bus, high Z, high impedance, and neither low or high will pass through. Okay, here I'm showing a little diagram of discrete decoders. A discrete decoder will have inputs, and those inputs will be unique, just like a combination lock, to get one output. Okay, so all these, there's only going to be one combination, and we're going to do this logic circuit with gates. Okay, in order to design a discrete decoder, we have to start with our output. And we're going to be asked for sourcing or sinking, and depending on what gate we have and what I request, we're going to choose a gate. In this case, we're going to do a sourcing. And I chose a NOR gate. So 0, 0 equals 1 is our unique condition, and that's going to light our LED. Okay, the next thing we need to do is select our input devices. And we're going to look at our code, and we always have to have the same code going into each gate. And they have to be the unique condition. So here we have an AND, 1, 1, 1, an OR, 0, 0 equals 0. So we're going to have to set these up. This is the input code requested, and we're going to have to make the gates match, and then make sure that they're the unique condition. Okay, once we have our output and we have our input, then we have to do an interface here some way or another to make these connect. So here I have an out 0 and an out from F, so I'm going to go ahead and use an OR gate, which is going to give us a 0 is what we need on our output device. Since this is a 1, I'm going to put an inverter in here in order to make it a 0 to match this. So we have to match it front to end in order to get that unique output. Okay, we have a discrete decoder here, and we want to figure out what the input code is. So the first thing we have to go to is the output. And 1, 1 is unique condition for this, and a 1 output is going to make that light up. So this is unique condition 1, 1. This is a 1, 1, 1. Okay, so we have a 1 here, obviously. 1, 1's our unique condition. This is going to be a 1. This should be a 1 in order to make that happen. And our OR gate would be 0, 0 equals 1. So that looks correct. And it appears that we did a good job. Looks the same. Okay, so let's design a discrete decoder from our code here. And it's a sourcing mode, so I'm going to choose a NOR gate. Kind of an ugly NOR gate. And so we're going to have 1 out, so that is obviously sourcing. So let's put a resistor and a ground. Okay, so this is going to be what? 0, 0, 1. So let's go down here. A, B, C, D, E, F. So this guy is going to be a 0, 1, 0, 1, 1, 1. So let's use we'll start with a NOR gate. Zero, 1, and we'll take C, move them up there, and that's also going to be a 0, and let's use a NAND gate. So we got a 1 out of there and a 0 out of there. So this guy could go directly here. And so what are we going to use here? We're going to use let's see here. We need a 1 out because we're going to convert it up there to a 0. So I'm going to take this 1, connect that to a, what would 1, 1, 0? It would be a NAND gate. 1, 1, 0. Let's see how we did. And looking at our beautiful CAD rendition, it looks fantastic. We did good.